Hello, this is a video on precipitation reactions. I'm following Brown, LeMay, Burston, and Murphy's chemistry, the central science. And this is near the beginning of a chapter on aqueous kinds of reactions. Okay, precipitation reactions. What's a precipitate, you ask? Well, a precipitate, first of all, a precipitation reaction is one where there's an insoluble product that results from the mixture of two clear solutions. So you've got clear solution one, you've got clear solution two, you mix them together, and all of a sudden something appears. Where'd that come from? And you realize, of course, that there must have been things that were present in the two solutions that you couldn't see, and that when you mix them together, they become visible. It's like magic. Maybe it is magic, or it could be chemistry. And so the precipitate is what comes out of solution when you mix those two together. The resultant product is called a precipitate. All right, here's an example. So let's say you've got magnesium nitrate in solution. The AQ stands for aqueous, so it's in solution, in solution, in solution. S, solid, not solution. Here's our precipitate, right? So we take this, and by the way, soluble means that it dissolves in water or in something. Insoluble means it doesn't dissolve. Well, the part that comes out as solid is the part that is insoluble. Infamous, more than famous, infamous, Three Amigos, never mind. Okay, so magnesium nitrate. So this is soluble in water. So you got it in there in the water, and then in this solution. And then you've got sodium hydroxide. And so when you mix these two together, well, hydroxides tend to be insoluble. There are some exceptions, but this hydroxide ion, obviously sodium hydroxide is an exception because sodium is an alkali metal in the first column. But hydroxide ions tend to be insoluble. And so when you mix these together, out comes the magnesium hydroxide, okay? Becomes a solid. Now, the sodium, we're going to call these spectator items in a second. They're just watching. Sodium's watching. But anyway, the nitrate is watching. The nitrates are almost all soluble. And as we've already mentioned, that sodiums are soluble because they're column 1 in the periodic table. So this is an example of a precipitation reaction where a precipitate comes out. It's also an exchange reaction, which brings us to our next slide, which talks about exchange reactions, also called metathesis reaction. Metathesis means we're going to switch partners. I could go into some kind of a dating or swinger kind of illustration that would be probably inappropriate. So let's not do that. So an exchange reaction is basically where switch your partner. So the A came into the dance with X, but A is leaving the dance with Y. And B came into the dance with Y, but B is leaving the dance with X. So we have a swing your partner round and round, exchange. We exchange the partners. So here's another example. I mean, the one we just had was an example. Here's another one. Silver nitrate. So silver nitrate, because nitrates tend to be insoluble, right? And so silver nitrate's there, it's insoluble. And actually, hold that thought, nitrates are always insoluble. I looked it up. Nitrates are always insoluble. And so the potassium nitrate on this side is going to be in solution, aqueous. It's going to be soluble. And silver nitrate is soluble. But silver sees that chlorine and says, let's precipitate. And so we have a switcheroo here. We have an exchange. The silver comes in with the nitrate, but the silver leaves with the chloride. The potassium comes in with the chloride, but leaves with the nitrate. And so this is the precipitate, silver chloride. Potassium chloride was in solution, but it ends up as silver nitrate. Now, some of these are ions all the way around. We call those spectator ions because they're not doing nothing. The nitrate doesn't want to dance, and the potassium doesn't want to dance, and the nitrate doesn't want to dance. But the silver and the chlorine want to dance. Okay, so that's an exchange reaction. How do we come up with this? Well, first we find the positive and negative ions. I always say cats are positive. So the cations are the positive ions. The negative ions are anions, but I would have gone to a different line and messed up my PowerPoint, so I didn't put anions down there. But the cats are positive. Cats are positive, right? Have you ever met a cat that wasn't positive? Yeah, probably. Okay, so find the positive and negative ions, and then swing your partner. You know, switch out the negative. I could have said switch out the positives, but basically switch the anions around and balance the equation, because sometimes you need to add a 2 in front or something like that, so that we have the conservation of matter. But okay, so exchange reactions. Now, what we've been drawing here are well, we can write them as ionic equations by splitting out the ions. A molecular equation, what we've been writing are molecular equations, because the molecular equations present the equations in terms of molecules. So all of these are presented in terms of things that are together, right? I didn't break out the ions. Break out the ions. So again, I didn't break out the ions here. So these equations we've seen so far are molecular equations. However, we can break out the ions with a complete, here's a complete ionic equation of lead nitrate and potassium iodide. So when they come into the dance, lead nitrate comes into the dance and potassium iodide comes into the dance. These two come in together and these two come in together, and they're all in solution. But when we mix them together, the nitrate's going to stay in solution because all nitrates are soluble. Potassium is a column 1 metal, alkali metal, so it's going to stay in solution. But lead and iodide, man, they want to get together. And so they form a precipitate. They form a solid. And so this is a complete ionic equation because all the ions are separated out as ions, although we do have the solid together as the molecule it was meant to be. It was a match made in chemistry. Now, these lead, nitrate, I'm sorry, not lead, nitrate, potassium. Yes, the nitrate and the potassium are spectator ions. They're not doing, they don't dance. They just sit and watch. So it came in as a lead ion, not lead, came in as a nitrate ion, it leaves as a nitrate ion. Came in as a potassium ion, it leaves as a potassium ion. Those are spectator ions. The real business is with the lead and the iodide. And so if this is the complete ionic equation, here is the net ionic equation. Just the dancers, please. So the lead and the iodide, they want to dance. And so there is the net ionic equation. This is the complete ionic equation. So writing net ionic equations, first, balance the molecular equation, okay? Then break out the ions. Now, by the way, you only do this with strong electrolytes. You wouldn't write an ionic equation for weak electrolytes. It's the strong electrolytes that merit an ionic equation. Cancel out the spectators. And there you have the net ionic equation. I think that's it for this video. Let me just do a quick thought and I'll be right back. I knew I was forgetting something. One last comment. If every ion in a complete ionic equation is a spectator, then no reaction occurs. We end up with the same ions at the end that we had at the beginning. Okay, this has been a video on precipitation equations, precipitates, exchange reactions, and ionic equations.